Good morning, everyone. Let's get started. So, topic for today, we're going to get started on congestion control. And why is my clicker not working? Okay. So this is one, as I mentioned last time, kind of one of the core topics in networking, very much like routing. It's also, I think, here at Berkeley, we probably cover congestion control in far more depth than any other undergraduate class I've seen. But I think it's both an important one and also a fun one. So hopefully you agree with me at the end of this. The plan is for today, we're going to just go over the basic building blocks, so the concepts in congestion control, very much like we did with reliability. And then Thursday's lecture, we're going to do a deep dive on how these are used in TCP. And it's very intertwined with how we do reliability in TCP. So if you're still a little confused over sliding windows and timers and duplicate acts, we're going to be looking at the two in combination in Thursday's lecture, kind of stepping through examples. And then Tuesday's lecture next week, we're going to touch on advanced topics in congestion control. So with that, congestion is an issue that we raised way back when we started this class in lecture 3, where if you remember, we said if you're at a router and you get two packets arriving at the same time, the router buffers one packet and transmits the other. And we said if the router is getting too many of these packets coming in back to back, then your queue is going to build up, you're going to get increased packet delay, and eventually you're going to have to drop a packet or you get loss. And so that's the regime in which we say that the router is experiencing congestion or your network is congested. And avoiding getting into that situation is exactly what this topic is about. And why is congestion something we worry about? Why is it harmful? It's obvious, but just to reiterate, it's because congestion can actually quite significantly impact performance. And so to give you some intuition for this, what this graph here is showing you is a theoretical model if you modeled the network as a queue, where you have a link of a certain capacity and a queue sitting in front of it. And if you said you have traffic coming in that is bursty in nature, which we've said that internet traffic is bursty, then what you get if you plot the average packet delay on the y-axis as you increase the load on that queue on the x-axis, and the dotted line here, the vertical dotted line, is the capacity of the link. What you get is delay that looks like what this graph is showing you here, where it's really rising up. And the two things to take away from this graph, without getting into queuing theory or any of that, is one is that, fundamentally what we're looking at is a trade-off. That as I increase the network load, we would all like to run our network at the maximum capacity, right? Have perfect utilization. What this graph tells us is you're not going to get that without trading off delay, without incurring actually pretty bad delay as you get close to the capacity of the link. And so a lot of congestion control is finding kind of that sweet spot where you want to operate, where you're getting full utilization of your network, but you're not going delay to a point that's unacceptable for applications. Okay? So that's one takeaway from here, is internalize that there's no perfect utilization and perfect delay. It's where you want to operate on this curve. And the second is that what I'm plotting here is delay. And remember that loss follows delay. So by the time you see a packet loss, you're already in this bad regime of delay. So loss is actually really bad if you care about delay, because you've already suffered the delay if you're seeing loss in your network. Okay? A little bit, I just wanted to start with some history on where congestion control as a solution and as a field came up. TCP, interestingly, in the when people started developing it, so we talked about Windsurf and others building TCP in the late 70s, all the way up to the mid-80s, TCP actually implemented no form of congestion control. The only thing that determined the rate at which a sender would send traffic into the network was the flow control that we discussed last time, where the receiver has an advertised window depending on how much buffer space it has, and it tells that advertised window to the sender. And then in the old versions of TCP, the sender would just dump an entire advertised window's worth of traffic into the network. When it had a timeout, it would just keep retransmitting an entire window of traffic into the network. And the internet was working just fine with this kind of behavior until about the mid-80s, where there was a series for a period of time of what the users of the internet and the people developing the internet observed what they called congestion collapses. And I just cut-pasted the text here from a few of the people who were observing this, and dealing with it and how their description of what they were observing. So this was Michael Carroll and Van Jacobson, who were both working on the Berkeley Unix system and developing TCP/IP within Berkeley Unix here at Berkeley. And what they saw here, as you can tell, is that the throughput going between the Lawrence Berkeley labs, so just up the hill from Soda Hall, and Berkeley dropped from 32 kilobits per second to 40 bits per second. And they were seeing this persistently for weeks. And so, 40 bits per second is pretty much, it's a non-functioning network. I know you're probably thinking even 32 kilobits per second doesn't sound like much, but that's what the internet was doing, or that's the performance you were getting from the internet at that time. So it was a 1,000-fold drop in throughput. And they were curious, so they, as you can tell here, they say they were fascinated by the 1,000-fold drop in throughput, and they set out to try and understand what was going on the internet. And these were the folks building the networking stack, so they were concerned that they had put a bug or done something wrong in the implementation. And along the way, they found a couple of issues that they fixed. One was with timer estimation. So the timer estimation you studied in section, we've covered it in section, that you did in section just yesterday, you should have learned how you were doing adaptive timer estimation. The original TCP implementation didn't have that. And so especially as the network was getting congested, delay was building up, but the timeout value was not adapting. And so it continued to have this short timeout and was dumping traffic into the network. And so Carroll and Jacobson fixed the timer estimation algorithms. But in the process also what they realized is that as more users were using the internet, sources were not slowing down the rate at which they were putting traffic into the network. So they were not doing any of what we now call congestion control. And so they put in a series of algorithms that we now call congestion control, and it's an entire field, into the TCP/IP stack in the BSD system. So if you look up on Wikipedia, Michael Carroll and Jacobson are both well-known figures in computer science. Michael Carroll was actually an undergrad here at Berkeley at the time he did this work. He was in the bio department, or microbiology department, I believe. But he discovered that he enjoyed hacking, and so he kind of drifted over into computer science. And Van Jacobson was a more senior researcher at the Lawrence Berkeley lab. And Carroll's, if you look him up, he was actually ended up being the chief architect for Berkeley Unix. So direct impact on Mac OS, Windows, Linux, all of those systems have a legacy that comes from Carroll's. Van Jacobson is as famous in many ways as Carroll's. I wanted to elaborate a bit because his contributions to networking and congestion control in particular are really noteworthy. He was leading the networking group at LBL at the time when they did this work about putting in congestion control. He has since had many contributions to the early TCP/IP stack and is the creator of many of the tools on the internet that we use, traceroute that you used. TCP dump is another tool that allows you to look at TCP packets. Berkeley packet filter that is widely used everywhere that allows you to filter out certain traffic depending on certain patterns in your OS. He left LBL after quite a while there, then ended up as chief scientist at Cisco, did a bunch of startups along the way, and now, like many people, is at Google, where he has, interestingly enough, he's fairly senior at this point, continues to work on congestion control. So his latest piece of work a few years ago was BBL. It's a new congestion control protocol. We'll very briefly touch on it. This is the congestion control protocol that is now underneath YouTube, Google Search, and really an increasing fraction of traffic on the internet. So really quite remarkable in his contributions to congestion control. So with that, what was their approach? Their approach is beautiful in a certain sense of simplicity, was an incremental extension to what TCP was doing already. So they said, looking at what TCP had in place, TCP already had ways of detecting loss. Right? We discussed this when we did reliability. Either you time out or you have duplicate acts, but TCP had that mechanism in. And TCP also already had a mechanism in place for Windows that controls how much traffic the sender puts into the network. So their basic idea was to have the source adjust its window size based on loss. So it's really as simple as that at some level. I think what was great about the solution was it was both a pragmatic solution, for reasons I'll get into. It was also an effective solution. The minute their patch was in, congestion collapse went away and the internet started functioning well again. We've never had a congestion collapse incident happen on the internet ever since the mid-80s. It was pragmatic in the sense that the solution they came up with required no upgrades to routers or applications. And actually, you don't even have to upgrade both sides of the TCP connection. You just need to upgrade the sender side. And it was really a patch of a few lines of code in the Berkeley Unix code base. And so in a matter of months, pretty much everyone on the internet had adopted their congestion control algorithm and was running it. So it's a nice lesson on wisdom in system design. You'll always hear, and I also strongly believe this, that the best solutions in computer science emerge from a real need and a concrete understanding of the problem. This is one of those nice examples of Carroll's and Jacobson doing that. And it kind of goes beyond because Jacobson was a physicist by training. And so when you read his papers on congestion control, especially the early paper that I showed you a snippet from, he thinks very much in a way like a physicist. He has in his head this, not complicated, but fairly sophisticated model of the internet as a feedback control system that has to respect what he calls a conservation of packet principle so as to avoid congestion. But he doesn't try and build that complicated mathematical model into TCP or into Linux, well, Unix at the time. Instead, what he took from that fairly fancy model was a heuristic that captured the core intuition of what that model was trying to do. And when we'll get to it next lecture, it's really a few lines of code changed, probably 10 lines of code that changed in their network stack. So quite impressive in that sense. Since that work, congestion control has been extensively researched and improved upon over the years, going back to '86. There are many, many variants of how TCP does congestion control. We are not going to talk about all of them. We're going to talk about one fairly prototypical solution. If you understand one solution in depth, it's not difficult to go from one variant to the other. You can pick up other variants quite easily. There are also radically different approaches that address congestion control completely differently from how TCP does that. And we're going to touch on them in our advanced congestion control topic. A lot of those ideas are actually now increasingly relevant in the context of data centers. And now that we have more advanced routers, some of them look increasingly practical. And so I think it's useful to know those. So with that, congestion control, more generally, there's a huge literature on the problem. This is one of those topics that everyone likes to work on. So the systems people have been doing congestion control forever. The control theory folks that study queuing theory and feedback control systems also have worked on congestion control. The game theorists, when I was a student, there was an entire course at Berkeley on the internet and game theory, taught by Christos Papamitru, who was a theory professor. So that's how congestion control occupied 50% of those lectures. And there's folks in statistics as well as economics. Essentially, you can think of bandwidth as a commodity or resource here. So you can see why economists would be interested in this question as well. Within industry, there's always been people working on congestion control. If you work on, if you're a vendor of an operating system, if you're a cloud provider, if you're a content provider, congestion control impacts performance. And so this is an area they look at. The last 5 to 10 years, there's been a real increase in that interest in industry. So if you look at any of the large cloud providers or content providers, so Netflix, Facebook, Google, Microsoft, they all have fairly large teams that are really just working on congestion control. So the last congestion control meeting I joined at Google, there were about 80 people in that group meeting. So that's how much of a topic it still is. The reason why we see a return of interest shouldn't be too surprising. It's that everyone's competing on performance. So there's just huge pressure to improve your performance. And congestion impacts your network performance. And your network performance impacts the performance of all your applications. So getting at that foundational level is important to all of these providers. The other is that new contexts, and notably in that data centers, because congestion control was originally designed for the internet, where you have large number of users, you have round-trip times that vary from microseconds to hundreds of milliseconds. You have just a very wide range of behavior and environments. Data centers actually, people know a lot more about that environment. Your round-trip times are typically tens of microseconds. You know the sources, you control them. And so there are certain aspects to a data center that you can exploit in designing your congestion control scheme that allows you to further optimize it for your specific environment.